but it might be a problem for some people, so we just added it.
I think it's a good idea. Yeah, it occurred to me after we put together the spec that, so you have this image and it's going into this VGG network, and then you're extracting these statistics and constructing your loss function. If you're not careful, when you do backprop, so backprop should go from your loss function through the statistics, back to the network, back to your image. If you're not careful about how you set up what's training and what's not training, you'll train the VGG network too. Right? So you like undo all the pre-training that's been done. So don't do that. Just a word of caution. Yeah?
This is just, I appreciate the steps for completion of this lab section in the specs.
Okay.
I don't think we've had that before, and I always, the first thing I do is go through and like figure out what do I need to fill in versus what's been made.
Good.
And it was nice to have that.
Good. Okay. Thank you. Kudos to our TAs. Okay, any other questions? Or have you guys started? Okay, okay, good. Yeah, good.
For the loss of style, should we be doing weights similar to the way we've done weights before? Or
So you mean in the loss function, there's this sum of terms and they're weighted?
yeah.
Okay, so if you read the paper, what they're doing is they're summing over all the layers and extracting style statistics from all of them, but then they're summing, and most of the weights are 0, except for weights on the layers that they want. I think there's 5 of them, and then they just use 0.5, like 0.2 for the weights. So the weights are uninteresting here, and they're not adjusted, they're not learned, they're just fixed. It's just some constant somewhere in your loss function that essentially doesn't matter.
So, what's on the specs now, part of it I really like is where they give us like at least that kind of stuff of like what our stuff should look like. But when we actually get to the optimization step, I still don't know what exactly stuff should look like. So how we're supposed to call Adam, or there's just kind of like lots of ambiguity of just not even how to do the lab, but like how you structure just calling of the functions to call them. And I think that would be helpful. Because I ask questions with TAs, and I'm sure 70 students ask the TAs the same questions of, oh, how are we supposed to call the function?
Oh, but you figured it out?
Yeah.
This is not a question, this is a comment. Okay. Okay, thank you. Yeah, we'll try to try that. Good.
I think one of the problems I'm encountering right now is, so I passed the content style image through BGG and pull out those things, right?
Okay.
And so when I go to run optimization on the generated image, it'll head through the network again, pull out and run MSE over those features, and there'll be 0, i.e. the tensors that I pulled out from before suddenly became exactly equivalent to the tensors that I just ran through the network. Is that like a drawing PyTorch kind of thing, or just wondering if that's something
I have no idea.
I had this, like, when I was first training, I had some zeros. And then I looked at them, and they were just really small numbers. And I dug through it, like, really small, especially on the space for style statistics.
It's literally like tensor dot equal other tensor is true. They're literally the same tensor.
Oh,
Okay. Yeah, then I don't know, I can't debug the whole thing without seeing your code, so sorry. But let us know if you can't figure it out. Yeah?
Quick question about the final project.
Yes?
Can it be a group project, you said? Or
Yes,
is it
so final projects can be group projects.
up to
Totally.
like how many people?
What?
Like up to like how many people? Or
Up to how many people? I haven't thought about that. I mean, the purpose of the final project is to make sure that you do something amazing and interesting. And as long as everyone's pulling their weight, I think it's fine to have a larger group. I think that's totally fine. But each individual needs to put in their fair share of that. So I think group projects would be of larger scope than other projects. But yeah, I think if you can accomplish more by collaborating, I think you should try. I think you should do it. Yeah.
does it matter which layers we're using? Do you have to use the same ones as the paper for content style? Or?
You don't have to. So I would recommend starting there. I think because if you use the sort of the correct layers, we know that it will probably work. Whereas if you go rogue like that, I don't know.
So it still works, it just looks really bad. Like, if you don't get like that style to work the way that it's supposed to, you can put
Yeah, it'll look different. It might not look style. There might look two styles. You know, all sorts of things. Okay, great. Let's move on then. Unless you have other questions, please let us know. Okay, so last time we finished our discussion of style transfer. And who can summarize in 10 words or less the entirety of those 2 lectures?
Loss function.
All right, great. It's all about the loss function, right? So the purpose of those lectures was to help broaden your mind about what a loss function can be. And just a reminder that loss functions encode what we want the network to do. Now there's a sort of a different way to think about getting the network to do what we want it to do, and that's regularization. So we're going to talk about that today. We're going to talk about classic regularization, sort of from a statistical learning theory perspective. We'll only touch on that very briefly, and then we'll move on to more DNN-style regularization. And we'll motivate that first by talking about overfitting. So I've used this word a couple of times in class. If I say overfitting, who knows what I mean? Everybody? Anybody like not know what I mean? Oh, okay, so maybe we'll just do like a one-slide introduction to overfitting. So imagine I give you some data. Here's some data. X, Y, we're trying to predict Y as a function of X. And let's suppose I give you 2 candidate functions. So I have 2 learning algorithms. Both learning algorithms look at this data, and they both come back with slightly different answers. Okay, so function 1 looks like this crazy, I don't know, polynomial. Function 2 looks kind of linear. Which one do you think is better?
Function 1, 0 loss.
Ha, okay. So Jacob. Jacob has, perhaps jokingly, suggested that function 1 is better. Why do you think function 1 is better?
Well, I mean, looks like it passes through all the points.
Passes through all the points. So what's the loss of function 1?
0.
Probably about 0. Is that good or bad? Okay. It's your question. Okay. Who thought F2 was probably better? Okay, go ahead. Can you defend F2 for us?
I could make F2 on paper. I don't need a deep neural network.
Okay, so F2 is super simple. Well, okay, so I think most of you, when I asked you the question, you said you thought F2 was better. Can you quantify for me why you thought that? Say it precisely.
Well, it's very unlikely that you expect the trend in your data to look exactly like F1.
Okay, so you're saying something about your Bayesian prior distribution over functions says that this function just doesn't seem very likely.
Yeah.
Okay?
Additionally, if you were to like add another data point in there, the likelihood that it actually fits on F1 is probably a lot lower because it would show that it's really overfit if you took another one and it's not even close to the rest of those. Right?
Okay.
So if you took one and it ends up like closest to the green line, you're like, okay, yeah, F2 is more likely. But if you were, it basically proves that this is overfit if it's hitting it exactly and it's a very complex kind of.
So you're saying something about an expected data distribution. So you were saying something about the shape of the function. You're saying something about, boy, it just feels like if I get another data point, it's not going to land on that. So you're saying, I sort of understand how data is distributed, and it just sort of never looks like that. Or something like that. Something like that. Okay. So you have a prior over data, you have a prior over functions. Go
Kind
ahead.
of a different way of saying both of those. I mean, we're assuming, I guess, that there's some sort of underlying, there's a true function here, some sort of underlying mechanic that's distributing the points. And, I mean, based on, just what there are lots and lots of functions in the world that are linear, and there are only a few that would be that exact shape. Or even if it, and because that shape is so particular for F1, even if the linear is horribly off, it's probably closer to, to lots of different functions than F1 would be.
Okay. So you're saying F2 is sort of a more common looking function.
Yeah. So
there's only one that looks like F2 though, of course.
Well, yes, it's true. But basically what you said though, it's according to our Bayesian prior that there are lots of believe that linear functions are pretty common because they're simple and we see them a lot. So.
Okay, so you mentioned a very important word, which is simplicity. So you think that simple functions are more common than complex functions?
I think that if you don't have enough information to infer complexity that you're probably going to be wrong. If
Okay.
you're trying to assume complexity, then there's lots of complex things, and it's hard to guess the right one. Whereas if it is simple, at least you have a good chance at it.
Okay, so you're saying something about maybe risk minimization. You're saying unless you can justify the complexity from a statistical perspective, like I don't want to commit to anything that the data doesn't justify.
Yeah.
So you want to make maybe as few assumptions about the shape of this function as possible, and you're saying something about F2 is like information minimizing.
Yeah.
Like I'm somehow making fewer assumptions if I use F2 than if I use F1, given the same amount of data. And that's your justification for preferring simplicity over complexity. Okay? I just put a lot of words into your mouth. I'm not sure if that's what you said.
No, that's spot on.
Okay. Okay, go ahead.
Not knowing what these data represent, my inclination is that there's probably going to be some noise to it. So the fact that F1 is perfectly fitting and has like basically a loss of 0 is kind of troubling, because even the best model is not going to have that, right? There should be some error that we're seeing just by virtue of the measurements we're taking.
Okay, so you're like actually worried. You think that no loss is actually an indicator that something has gone wrong because you just don't believe in clean data. Okay. Okay, last time. Go ahead.
There seems to be a pattern where the points are going up the further right you go, but F1 doesn't capture that at all. So if we were to grab a point a little further to the right, we would assume we go way down, which just by intuition it doesn't look like that's what the points are doing.
Yeah, or maybe or maybe another way to say it is if this point had been jiggled just a little bit to the left, the value of the function is going to be like way down here. And that just feels weird to us. I think like, boy, most functions don't work like that. This thing is going to generalize in some crazy manner off to negative x. We don't know quite how. Okay, I think you all have the right intuition. Here's some more samples. You know, of course, if you see samples like this, these samples are quite bad when compared to F2, but quite good when compared to F1. And sort of the idea, the theme of regularization is to try to put numbers, what you've all just said, to somehow favor simpler hypotheses over more complex ones with an eye towards fitting the pattern in the data and not the noise. Of course, those are a bunch of vague words, and it's not clear how to do that. But generally, we want to somehow favor simpler models. And regularization is one way to do that. So there's a lot of different ways to think about this. My personal preference is to think of it in Bayesian terms. So you can imagine that we all have priors over these functions, and you've talked about some of them. We think that linear things are just generally more prevalent. We think that simple things are just a priori more likely. And one way to think about regularization is as a prior on functions. And we penalize things that are too complex. The advantage of a Bayesian formulation is that there's a very natural mathematical framework to help us trade off the fit to the data and the penalty we get for violating the prior. And Bayesian optimization and learning will help us do that naturally. There's other ways to favor simpler hypotheses, and a big one is called sparsity. So we talked about this very, very briefly at the very beginning of class. I showed you this slide. So when we think about a loss function, we generally think in terms of some function and some input and some weights and some target, and we like have some maybe hinge loss or I don't know, softmax, something or other. These terms in our loss depend on data and our learned parameters. But regularization terms typically depend only on the parameters of our network. And there's lots of different types of regularization. So we talked about these briefly, but here's the sum over all the weights in our network, and we square each one. So this is equivalent to putting up like a parabola on all the weights of our network. And you already, I know you know this, but just tell me anyway. So what happens if, let's suppose we didn't have any of this loss. Let's suppose all that was gone. What would happen if our only loss term was this squared thing here? What would happen if we optimized? All the way to go to 0. And the same thing is true. So that's called L2 regularization. And there's lots of reasons for that. We won't go into them in this lecture. But one way to think about this is we have a Gaussian prior on the weights of our network. And that Gaussian is centered at 0. And so the most likely setting of the weights is 0. The reason for this is, we can go through the derivation someday, but this is, you can think of this as the log of a Gaussian over weights, with all the constant terms dropping out. Okay, so L1 regularization, same idea, except instead of squaring the weights, we take the absolute value of the weights. You might think, just looking at that, that's pretty much the same. I mean, squared error looks like a bowl. Absolute value kind of looks like a V, but essentially the same. Turns out these have very different properties. And we'll talk about what some of those properties are in a minute. And then there's this thing called the elastic net regularizer, which is a combination of both of those together with some sort of scalar thing that balances the two. And that also has its own properties. So I thought I would take you through a little bit of a case study on the differences between L1 and L2. Like I said, the mathematical form seems very similar, but what happens when you actually run it in practice is very, very different. So this is a beautiful example from Hastie and Tibshirani's statistical machine learning book. So here's two figures. And what this is showing coefficient magnitude as a function of the strength of the regularizer for two different regularizers. And the idea is we have all these predictive variables, and we're trying to predict whether or not someone has diabetes. Okay, so this is a supervised machine learning problem. These come in, diabetes comes out, but we're not showing any sort of loss. What we're showing is what's the magnitude of the coefficient on a particular predictive variable. So for example, age. And what this is showing strength of regularization, where as you get down here, the regularizer gets stronger and stronger and stronger. So what happens to the coefficient on age as regularization gets stronger and stronger if we're using L2 regularization? It gets smaller and smaller and smaller. And it traces out this kind of odd-shaped path. But eventually, if we increase the regularizer all the way to as far as it'll go, what happens? It goes all the way to 0. Okay? And notice that essentially at no other point does the age coefficient equal 0. Maybe it's 0 right there, but probably not. It's probably just close to 0. And that's true for all of these variables. As we increase the regularizer, they all get closer and closer and closer to 0. Some of them actually even change signs, but none of them are equal to 0. Now, yes, go ahead.
What's the red dotted line again?
Actually, I can't remember. That's not relevant to the purposes of this discussion. It's probably something like optimal regularizer or something. I'm not sure. That's not the point. Okay, so let's compare that with what happens with L1 regularization. So someone described to me in English. So same model, same data. All we did was we changed that regularizer from an L2 to an L1. Yeah, go ahead again.
Nothing changes sign, and they go to 0 at different spots.
They go to 0, and then what happens once they go to 0?
They stop.
They stay at 0. And it turns out they aren't exactly 0. Okay? And so what does this tell you about, let's suppose this dashed line right here is, let's assume that this represents the optimal predictors. What does that tell you about the age variable? Age variable is irrelevant to predicting whether or not you have diabetes, according to this model. It is exactly 0. Its contribution is exactly 0. Not close to 0, exactly 0. Similarly, LCP. I don't know what that is. Lower cholesterol platelet count. So it's also irrelevant. LBPH. I think that means that it's 0 at this point as well. But how about weight? Weight matters for the optimal model. Of course, if you increase the regularizer too much, everything goes to 0. Nothing is important. But the point is that L1 and L2 have very different properties here. And what accounts for this? So this is, by the way, this is called sparsity-inducing regularization. So this regularizer tends to induce sparsity. In other words, it takes weights and sets them to 0, exactly 0. And what that tells you is that your predictors don't matter. They're irrelevant. Okay, so I thought we might like to build some intuition for why this happens. So plenty of people in machine learning, and deep learning in particular, use L1 regularization because of this property. Why, though, does L1 regularization induce sparsity while L2 regularization does not? Okay. Well, we don't have a whole lot of time to talk about this, but I thought maybe a picture would help. Here's a slide I found that attempts to explain this. Okay, so let's imagine that we have an L2 prior on weights, and let's imagine that we have a cost function that's also kind of Gaussian and mean squared error-ish. You can think of the overall cost as the sum of two parabolas. The weight regularizer is sitting here, centered at the origin. So if that was the only parabola, things would want to be centered at 0. But there's a cost function, and if we didn't say anything about the weights, the optimal answer would be right here. The true cost function is the sum of these two things. And so the optimal weights lie somewhere here. And it's sort of where these two circles touch. By the way, why are these circles? So what this is showing contours of equal cost, either from the sort of the loss, the model prediction, or the regularization. Why do they look like circles? Any thoughts? Good.
You said these are parabolas, right?
Yeah.
So if this is in, more than two dimensions, then this should be like a bowl going up, and we're just looking
Yep.
at the bowl from top down.
Exactly right. So we're looking at the bowl from the top down. Yep, go ahead.
Depend on your lambda, depending on which circle you're at.
So no, the lambda will scale one of the circles. So it'll take the bowl, and if lambda is really, really high, then what that means is that the bowl goes up very fast as you move away. If lambda is very, very small, it means the bowl is very shallow. So this is showing where the two bowls intersect. So if lambda is really, really high, then this bowl is going to be much steeper, and the two are going to intersect closer to the origin. Make sense? Okay, but I guess I'm asking, why is this a circle? So these are contours of equal cost. Any thoughts?
Well, I can see for sure why the yellow circle would be a circle, right? Because you have no reason to set preference on one leader over another in your regularizer, right? But I don't understand why. I mean, you can assume that your cost function is going to be circular, right, in terms of W1 and W2, right? But it really does depend on the data and how important each weight is.
Well, okay, so I guess I didn't
So you're assuming that
we're
W1
assuming
and
that
W2
the
are
cost
equal.
function is just simple squared error.
Yeah, okay.
And there's some true prediction that we would.
Okay, so this is some true weight we're going for.
Yeah.
And we're
Well, so this is some cost. This is some cost defined on the data. This is some cost defined as a function of the weights. But I'm just assuming that both are sort of parabolas. Okay.
Back to your question on why the red circle is a circle.
Yes.
It's just the sum of all the weights squared, so it's literally the equation of the circle.
Right.
1 squared plus weight 2 squared equals radius.
Give some radius. Okay? So this is important because, that's right, so these are circles because it's squared, because the regularizer is a squared thing. So it's just like Pythagorean theorem. The radius of a circle is x squared plus y squared. And if you trace out units of equal cost, you trace out circles. Okay. Let's see how that changes when we think about L1 penalty. So in L1 penalty, the story is a little bit different. So let's imagine this is our parabola representing the cost of some data term. It's the same in both of these. But here we're using L1 regularization. So why is this a diamond now instead of a circle? Yeah.
I kind of think of it in terms of like Manhattan geometry.
Manhattan distance.
Yeah.
Yeah. That's right. So this is tracing out a contour of equal cost. And when we're thinking about absolute values instead of squared values, the contours of equal cost look like this diamond thing. Okay. So compare these two pictures. Okay, you've got sort of these penalty or constraint regions. And here's why L1 regularization again, this is a little bit hand wavy, but I'm just trying to build a little bit of intuition. Here's why L1 regularization induces sparsity, whereas L2 does not. You imagine that this circle is getting bigger and bigger and bigger until it touches this bluish diamond. And you ask, where will they intersect? There's non-zero probability that this pointy part right here is just going to pop that bubble. Okay? So the fact that there's a point here, and the fact that that point is on this axis, means that this circle is likely to touch that tip. Whereas over here, the likelihood of this circle, imagine there's a balloon getting bigger and bigger and bigger, touching at exactly that point is essentially zero. So formally it's like a measure zero event. Like there's essentially no probability mass there, whereas here there is.
Interesting. So like and it touching that axis, it then intersecting at that axis corresponds to beta 1 going to 0?
Yes, beta 1 is 0. Right? Similarly, beta 2, if beta 2 was over here, if we touched here, beta 2 would be 0, beta 1 would be nuts. Right? So it's something about the geometry of these contours that induces sparsity. It's the pointiness of them. Okay, so this is a very classic look at regularization. What I'd like to do now is switch gears for the rest of the lecture and tell you a little bit about DNN-style regularization. So when we think about deep neural nets, it turns out we have all sorts of other options when it comes to how to penalize complexity. And so here's an early one that's still very famous called dropout. Okay. So here's the idea of dropout. Let's imagine that I have some neural net, got some inputs, some hidden layers, some output. And what I'm going to do is I'm going to randomly kill neurons. And I'm just going to take my inputs and then pass it through this sparsified network. That's it. That's dropout. Okay? So, what do you think? What's your reaction to this?
So is this specifically like in your entire neural net, you just kill neurons permanently, or is this when you're
Not
doing a
permanently.
forward pass?
Okay, so each pass through the network, we kill a random, different subset of neurons.
Okay.
Okay? And this is a regularization strategy. Why is this a good idea or a bad idea?
I think it's a good idea because then your network will never depend on too heavily on certain relationships that at any point you could just drop out the network. And so it'll force it to kind of learn other relationships and features that, and then when you're actually using it to predict you're not doing dropout, so it'll take advantage of all of those relationships that it's learned.
Okay. Okay, we'll have a lot to say more about what you suggested. So the suggestion is, well, this neuron here just can't depend on any particular subset of these features being available because we're artificially destroying them. Okay?
So for every pass you're going through and killing random neurons, you're kind of training smaller networks. So you can say you have
okay.
a bunch of smaller ones, and then at the end you kind of have like an ensemble of like, hey, what do you all?
Yeah, so you mentioned the word ensemble, so maybe you already have heard about dropout. But that is another interpretation of how dropout works, is you can imagine that if we drop out all of these neurons, this is a much smaller network, and you can imagine that training a small network would be a good idea. Maybe it's simpler, maybe it doesn't have as much complexity available to it. But because we do different subsets of neurons, we have many such small networks, and because we're tying all the parameters together, we're reusing weights across all of these, it's like this becomes what's called an ensemble method in machine learning, where we have an entire family of predictors, we're training them all simultaneously, and then somehow averaging their predictions back together at the end. Yeah, okay, good.
So then do you add back in the dropout weights after that pass through? Or do they remain at 0? Because it seems like you're losing a ton of information if you just set them to 0.
Yeah, so at training time, in the forward pass, we actually set them to 0, and then when we back prop, they're 0, so nothing about them gets updated. Now, of course, this is probably use stochastic gradient descent or something, and so yes, it's a very odd thing. So for that particular pass, the dead neurons did not get updated.
So when we were doing the cancer detection, some of the people didn't shuffle the image before running it, so it would overfit on the, like, it would get 100% accuracy because they would just keep getting the negative images.
Oh,
But
okay.
I feel like if you do like sort of a dropout thing, and then it wouldn't learn once the positive things came out because it was so sure that it was gonna be just no cancer. But I feel like if you did the dropout, then you would be able to slowly be able to learn because like you're zeroing out some of the neurons. But I don't know, maybe. So it wouldn't overfit so much on the negative.
Okay, so you're saying, I think you're suggesting that dropout is going to slow down learning.
Right.
And so if there's some weird data distribution problem, like we see all of our positives first and then all of our negatives.
Right.
Because dropout slows down learning, we're not going to overfit too soon on the data. That's probably true. Dropout probably does slow down learning, maybe.
So I think Jared just answered both mine and Song's question.
Okay.
What we were really asking is, we don't actually set the weights to 0. We zero out.
Yes, I'm sorry, that's right. We don't set the weights to 0, we zero out the activations.
Right.
Yes. Sorry. Sorry, that wasn't clear.
So, I mean, the way I'm looking at this, it both, discourages really, advanced specialization of any specific neuron, right? Because if a neuron suddenly gets all of its inputs that it uses to predict, whether it sees wrinkles, on someone's shirt or not, then it just can't do anything. But not so much that as I think it encourages generalization more, right? Because if, maybe a neuron learns that it can rely on 5 different neurons, to do the same thing, right? Then maybe it's just reducing complexity, I think, in that way.
Yeah, so I think a couple of you have said this, and I think this is the right intuition. So this is the way Jeff Hinton, who's one of the fathers of DNNs, thinks about dropout. He said, in order to overfit a function, if you want some neurons to do it, they have to collude. They have to rely on each other's weights, and they have to rely on those weights and activations being super precise values.
Yeah.
But if you do this, they can't. And so what this does is it forces the network to learn a distributed, it's called a population code, a distributed representation where information about what you care about is distributed among many neurons, and some subset of them may or may not be available. And so as a result, but because it's stochastic, you can't ever get super fine-tuned weights that are exactly the right number to fit the data in exactly a super precise way. Yes?
So ensemble methods generally are really good. Like, if you take a machine learning class, you know ensemble methods are good. But we started this lecture talking about regularization as we have this bias that simpler is better.
Yeah.
But how does an ensemble encode that? Like, it seems that ensemble is just more complicated, right? Incorporating multiple models.
Yeah. So the question is, how is it that ensembles, why would that idea encourage simplicity? Yeah, I don't know, what do you think? Go ahead.
So, we care about simplicity, not because we care about simplicity, but because it's a good approximation for, generalized. And so this doesn't seem simpler, but maybe it gets us closer to our goal of generalized.
Okay. There's a very specific technical, we've got a couple more hands. There's a very specific technical reason that we'll talk about in just a second, but I do want to hear what other people think. So go right back here, go ahead.
So the way that you combine those, so if you accept that the one with less neurons is simpler by itself, if you combine them all in a way that doesn't increase complexity too much, then it's not necessarily going to be that any more complex than the simple ones. Like we saw the fully connected neurons that didn't have the ReLU, and they're all linear, even though there was a lot of neurons, and there's maybe it might look like more complexity, we were combining them in a way that was linear that didn't actually add complexity. And so that's the same thing here. If you take simpler networks and you might combine them in a way that's I don't know that what this is doing, but other ensemble methods do that, where you combine a linear combination of their outputs, then they're just as simple as the simple ones that we were using originally, even though it's a combination.
Okay, 1 or 2 more comments. Did you have one back there? Go ahead.
In my mind, if I think about, we have multiple complex models that are overfitting to our data in different ways. If we average those, then we're going to get something simpler in the middle of all of them. That's when I visualize it in my head. If I'm averaging over
Yeah, okay, I think that's a good intuition. So I think I don't think there's like a right answer to your question. It's a really good question. The one technical thing that I will say is the following. If you're in some region of a cost function, so pretty much anytime you get to the bottom, like you've optimized models and you've sort of gotten to the bottom of a cost function, the cost function will look locally convex. So remember that convexity is the property that if you take any 2 points and you average them together, the function lies below those 2 points. And so one of the bases for the performance of ensemble methods is this fact. So all else being equal, if I have 2 models and their final cost is approximately the same, if I average them together, probably I'll get something even better because of convexity.
So it doesn't necessarily do with simplicity.
In this case, no. I think it's not quite about simplicity for ensembles. But something about this is a combination of these ideas, where we have a lot of simpler models, but they're tied together, but we're averaging them. Like, who knows? Like, I mean, so for me, this seems like super hackish. Like, I don't know who came up with this, but I think they just made it up and then justified it in a post hoc way.
And then it
probably
worked.
what happened. And they got a figure about it.
Now we use it.
So very, very simple though to implement this. It's literally like junior forward pass. You've got some hidden layer activation. You sample some random binary mask and you multiply it, and like they just go away. And then when you back cross, it kills the gradients. So we've talked about this. So we've talked about how this forces the network to have a redundant distributed representation. You can also think about it as an ensemble thing, etc. There was a very interesting analysis that I thought I should share with you about this. So I'll just read this to you. Actually, can I have somebody read this? So go ahead.
Dropout training falls into the broader category of learning methods that artificially corrupt training data to stabilize predictions. The effect of training with features that have been corrupted with additive Gaussian noise is equivalent to a form of L2 type regularization in the low noise limit. We show that dropout training is first order equivalent to L2 regularization after transforming the input by diag function, where I hat is an estimate of the Fisher information matrix. This transformation effectively makes the level curves of the objective more spherical and so balances out the regularization applied to different features. In the case of logistic regression, dropout can be interpreted as a form of adaptive L2 regularization that favors rare but useful features.
Okay. So this is just to say, I don't want to say too much more about this, but like I said, I think dropout seems super hackish. There's many different interpretations. No one's quite sure how to interpret it, but it seems to be super useful. And there is at least some theoretical analysis that suggests that good things are happening even if we don't fully understand it.
So why is dropout so much more effective than basic L2 regularization?
Yeah, I don't know. One possibility is that if you sort of imagine where L2 regularization happens in your model, it happens like way down here, and information from your regularizer has to somehow like propagate itself back through your model. Whereas here, multiplying activations sort of happens everywhere. I don't know.
So it could have better higher order effects even if they're first order equivalent?
I'm not sure. I don't know. I'm not sure anybody does. Okay, now, of course, you might be thinking, well, what do you do at test time? At test time, do we also drop things out randomly? Ideally, of course, we wouldn't drop out things at test time. This is only for training. And so at test time, what you'd sort of like to do is, you could imagine what we'd really like to do is sum over all possible dropouts. Sum over all possible dropouts. Well, there's an exponentially large number of those, so we can't do it. You could imagine, though, a Monte Carlo approximation to that where we sample a bunch of dropout masks and then somehow take our prediction through many dropped out networks and then average the results together and call that our prediction. And in fact, this is what people do. And in fact, what people do is they actually leave all the neurons turned on. They don't drop out anything. And evaluating the whole ensemble, but what they do is they actually scale the weights by the dropout factor. And I don't think we have time to go through this, so I want to move on. But what you essentially end up doing is if you drop weights out with a 0.5 probability, roughly speaking, the network has learned that there's only kind of like half as many weights that are going to be coming in. So if you turn all the neurons on at test time, it's sort of going to see twice as many things as it was expecting. So you sort of want to scale everything by a factor of 50%. So you literally just push things through, but then multiply by 1 minus whatever your dropout rate was. And deep learning frameworks like PyTorch and where's all this stuff? Things like PyTorch and TensorFlow will do that for you automatically. So you can specify a dropout layer. It'll ask you for the dropout probability, which is just a number between 0 and 1. And then at test time, it will automatically do that weight scaling for you.
Just a brief question. Where do you typically put like a dropout layer? Would that go towards the beginning or the end? Or
It's
just
pretty cool.